All right, welcome back. So we stay with the topic, backbone security in ISP networks. With me on stage is now Matthew Farrell. Please give a warm round of applause.
Hi everyone, and thank you for attending this talk. As the title say, we are going to speak about ISP networks and mainly about optical line terminal as OLT. Who am I? I do work for Quarks Lab adversary simulation team, mainly in doing pen tests and red team operation. And I'm going to present the result of one of our mission. In this talk, I treat optical line terminal as a key attack surface inside ISP access networks. OLT are not just edge devices. They control traffic and subscribe services. So a compromission of one device can affect a large group of customers and users. The main point is that the biggest risk comes from where the OLT stand in the network and how they are centrally managed. Because the infrastructure is trusted and centrally operated, one weakness, especially in the management plane, can scale into a fleet-wide control. As I said, OLT are not just large routers. They sit at a critical trust boundary between the provider core and many subscribers ONTs, the box in your houses. They control so many customers' connections that a mistake quickly become a large-scale problem. In many networks, the access layer is treated as safe by default because it's centrally managed, and security usually focuses on endpoints and internet-facing apps that make small flaws in this layer capable of causing real damage. For the rest of the talk, the focus is not just getting a shell on one device. The real issue is gaining control over provisioning, traffic policy, diagnostics, and life cycle of downstream devices. The reference device was from the vendor VSOL, but that not the main point is not the vendor. It's the shared architecture and the recurring weaknesses that keep appearing across different platforms. The access layer turns security problem into real-world impact. Availability issue can disconnect thousands of subscribers. Integrity issue can change policy across many lines, and confidentiality issue can expose traffic from multiple subscribers. The key scaling point is the fleet manager. Code execution or admin controls there, and you can use the same tools the ISP use. Bulk configuration, firmware updates, and telemetry, almost everything. In this research, the management product is vSOL Cloud BS EMS, but I will reference it as the fleet manager for the rest of the talk. Let's talk about OLTs and a quick GPON refresher. In the topology, the provider core connects to the access network through the OLT, and the OLT then distributes service over passive optical fiber line to customers ONT and ONUs. The fiber itself is passive, but at the operational layer, it's active through provisioning and configuration updates. In this tool, the main attack surface, as I said, is the management plane. For example, the web appliance. That include all the interfaces, the credential, and the trust relationship between the cloud fleet manager and the fleet of the OLTs. As an attacker, I really like to look at the vendor documentation because it clearly maps the architecture. It shows how components are connected, where the management sits, and where the trust is concentrated. So in this case, the OLT is already in a critical control point, but the fleet manager above becomes a real single point of failure. This is a threat model, and it comes down to two common entry points. The first one is a direct internet exposure of the management interface, whether by design or by mistakes. And the second one is an internet foothold that lets an attacker pivot in the management network. That's most of the time what usually happens during red team engagements. Anyway, in both cases, the goal is the same. It's to cross the management plane trust boundary and reach a high-impact control surface. The diagram here shows two main starting points for an attacker point of view. either an exposed OLT or an exposed fleet manager. From there, the attacker can follow the same management path as the ISP use. The key idea, as I said, is amplification. Compromising on OLT leads to the fleet manager, and once you reach the fleet manager, you can compromise the whole fleet. It also shows why diversity in devices matter. If different OLT models share the same weaknesses, that points to repeated design and implementation problems. And they keep appearing and appearing. Now we can move from compromising a single device to compromising the whole fleet. And this is where the small access is going to turn into a control of the whole fleet. So the fleet manager is the main scaling point for us, the attacker. It already has privileged accesses for provisioning, diagnostic, and firmware updates to all managed devices. And that's why the hardening device still matter, but protecting the control plane matter most, because the system that can manage everything can compromise everything, and that's what we are going to see. So as an attacker, before the analysis, the first step while doing reverse engineering is to get the software. In this case, the official Cloud EMS download path was known, but the related files, firmware, and stuff were no longer available. The vendor removed Cloud EMS software, but copies of source archive often remains online on mirrors, old file server, or forgotten hosts. Removing the official download link did not make the software disappear from the internet, for sure. But getting it became another CTF, as copies were still available elsewhere. As we can see, removing a link rarely stops the software from still being available elsewhere. So we use simple Google Doc technique to retrieve some of the components online. But unfortunately, the desired target, let's say a directory listing, was not available anymore. That's what we thought at first. Even if the domain went offline, historical references were enough to identify the host and recover the artifact, and we'll see how. Because this slide shows that the hosting site may look offline only because DNS no longer resolves or no longer works, while the server itself is still reachable via its IP. That meant content can stay exposed even after an organization believes it has been removed. And archived DNS record can help recover old IP addresses and quickly confirm whether the problem was only name resolution. So we unpacked the archive and start looking at what it was containing. So Cloud EMS used a common management stack design, a Tomcat web app, a MySQL database, and device management features such as SNMP to manage remote devices, OLTs. And it was packaged as a Docker, but essentially for deployment purpose, because the key point was not containerization. It was convenient and not isolation. So this slide shows the management plane risk in practical terms. You can see the Docker configuration on the right. Cloud EMS exposes the web interface and has direct access to the managed OLTs. And we can see that in the deployment, the Tomcat run with elevated privileges, the first red line. And down below, you can see that the Docker socket is mounted from the host to the container. With weak container isolation, a risky host access management compromise turns into a host full infrastructure compromise, because we will be able to escape the Docker container to go to the host. Privileged container may compromise much worse because they removed much of the expected isolation. If the management plane runs in a privileged container, a web bug leads to a full host compromise, and then you can bounce to the core network of the provider. So mounting the Docker socket into the container was a really bad idea, and access to the host Docker API was used for us to escape the container sandbox. So we performed an audit of the source code we retrieved. We decompiled the Java application and read it with whatever IDE you want. And the two most important weaknesses worked before authentication and were reliable. That's what you have to remember. The first was an authenticated information leakage, which helped us identify the target. And the second one was an unauthenticated arbitrary file upload, which gave us a pre-auth-write primitive inside the Tomcat, which led to like a server-side code execution. There were also other issues like hard-coded secrets, credential, authenticated command injection, but in practice, a single period flow is enough for us to compromise the target and break the trust boundary. Now we will see how the requests were handled. So Cloud EMS use Spring MVC and a central dispatch servlet, and use Apache Hero to control the HTTP requests through a filter chain. What does it mean? The idea is simple. All requests should go through this centrally access control, which is Hero. That makes the filter chain of this web app the key security boundary. If an endpoint is marked as anonymous by mistake or on purpose, or if path matching fails, it means we have a root bypass and the whole attack surface became pre-authenticated. This is where the first mistake becomes clear. In the Shiro filter chain, two sensitive endpoints were marked as anonymous, yes, in red over there. Slash system monitoring, get system CPU and mem, and slash upload BU file. This is not a bypass. Shiro simply follows the configuration and let us query these two paths without authentication. The third primitive is an authenticating information leakage. So the endpoint returns CPU architecture, memory data, along with runtime information. And those information are very important because it helps us fingerprint the targets, know if the target is alive, but also allowed us to craft a specific implant for the desired target during our red team operation. Also, I said it confirms the reachability. If the endpoint responds, the attacker already knows that first the target is alive, and then the target is vulnerable. This is what the info leak looks like. So a simple GET request returns a 200 JSON response. What matters, as I said, is the kind of information exposed, and especially for us, the CPU architecture. The second primitive is an authenticated arbitrary file upload. The upload handler accepts file without authentication, and it uses a client-supplied file name to write the file on the target. So we just use .. to go across the file system tree. And in the Tomcat environment, that means a file upload becomes code execution if you know where to write properly. And that's what we've done. On the Tomcat server, landing a GSP into an executable context directory make it like a primitive for code execution. So now the reliability depends on the concrete constraints. The write must not be confined to the intended upload directory, which it was not. And the file landing zone must be reachable. And for that, we just drop our web shell in the icons folder, the /image folder. So we have now a period file code execution. And once we proved that the code execution was stable, we knew we can bounce from the Cloud Fleet Manager to all of the targeted. So at this point, the containment changed because we also knew we could escape the Docker and we could bounce to the infrastructure of the provider. So now we're going to move from the Fleet Manager to the OLTs, which are generally more exposed online over the internet. So once the orchestrator is compromised, the OLT management plane becomes reachable through like the normal southbound connection, and usually through SNMP. So a direct access to the OLT is no longer necessary for the OLTs to be reachable because we can bounce from the manager to the OLT. So in this section, we will look at how to exploit vulnerability in the OLT to go in the other way, to compromise first an OLT and then bounce back to the fleet manager to then go back to all of the OLT fleet. First, SNMP expose writable diagnostic feature and configuration functions. Then there is a web interface with unsafe paths leading to call to system function without authentication. And finally, something funny, there is a feature called TACA CS authentication. And in that case, it became risky because the trust boundary and input labeling were badly performed. So we're gonna the weaknesses pattern across the ORT are sadly consistent. We also find default credentials and command injection everywhere, but they were not needed as we already have two ways of getting a shell. And I'm gonna maybe repeat myself, but this is like kiddie stuff. This is very not technical. SNMP. In most of the OLTs model we audited from this vendor, the traceroute feature exposed through SNMP ended up building a traceroute command with attacker control input. And the important part is that this pattern shows up across all of the models. So it strongly suggests that there is like either code reused, share mistakes, or they've been provided a compromised or like badly written SDK. But for us, as an attacker, it's like a gold mine because it's gonna make the effort of doing the reverse engineering like really, really, really easy. The call stack show like the path cleanly, the request come in, input gets stored, a worker is started, a worker thread is started to do the diagnosis feature, and the input are passed to the system function, and you have like a shell command. The important part is the validation failure, as I said. The code may confirm that the inputs look like a valid IP or host, but in the later original string is used in the shell context. So even if you perform like a validation of a string, if you reused the first string from the beginning, like the filter is useless. And other model, we saw an attempt to make this safer. They tried to implement a blacklist of dangerous character, and with something this blacklist we found across many embedded devices, and we will see like why one mistake make the filter useless. So the key point is that the command injection checker does not really help because it uses a weak blacklist. You can see on the right side. As always, the shell is the final execution point and the core problem. So in practice, those troopers are often just move the question from like, is there a call to system to can I bypass the filter? From a threat model point of view, this safe exec wrapper are usually the first stuff we are going to audit because for us they are considered as hotspots. If an attacker control input still end up in a shell and the only protection is the best effort filter, at the end, the risk is still there. So the filter uses small blacklists. It blocks most obvious character, like semicolon, pipes, but missed one, the new line. And new line can also act as a command separator in the shell. So that matters because the validation was also weak. They were relying on functions like anetiton and get host by name. And you have to know that these functions, they are not used for security purposes. They are only used for validation. Because what I'm going to show here is that the first part of the string is a valid IP, but not the rest. And the get host by name function or inetaton, for example, they're going to stop at the first not allowed character, and they're just going to treat the first part of the string. So they're going to ignore the /n touch TMP poon part of the string, and they're going to consider the 888 string as a valid IP, and then continue the execution. So a valid IP, a valid looking IP at the start, followed by an injected command, is enough for us to bypass the filter and perform the code execution. As I said, it was exploited through SNMP, so we had to find the OID for the request. And we not decided to perform reverse engineering of the binary. What we did, we looked at the web server written in Java, and we performed a Java reflection to retrieve all the OID at once. So in practice, reversing the whole ecosystem, and I mean by that, by the web server and the Java part, is often easier than performing the reverse engineering of all the binaries for all the different models. Now we're going to switch from the SNMP to the OLT web interface. So this is another management plane, and in practice, we found that it's easier to reach because we found out that a lot of OLTs are internet-facing. I don't know if it's by default or if the provider did a mistake. As I said, the stuff we found are also pre-authenticated. So the same pattern show again. You have diagnostic feature, auth feature that are calling system. So they are executing shell command. And there is no authentication. And I mean, they tried to implement session and stuff, but they were really useless. So even if SNMP is not exposed to internet or is locked down, we still have two more pre-authenticated way to compromise the OLT device. The first one is in Taka CS+. That one is funny because it's an authentication feature. And the second one is a traceroute diagnostic feature. In both cases, it's the same story. User input end up in shell command, and the offload is not performing well, so you have code execution. Let's look at the first one, the Taka CS+. As I said, it affects multiple models through the web route /action/main.html. And because it sits at the authentication path, as designed, it's reachable before login. So the pattern is a classic one. They take two get post parameter from the request, user and password, and they put them in a string, and then they invoke a binary locally to check for the Taka CS+ authentication to see if it's valid. And you just have like a code execution. And for the traceroute feature, it's the same traceroute feature, but in the web binary. So the flow is very similar. The request takes a destination from a post request, and at the end, use it in a system call. So they treat like user input in an unsanitized way, and that's why you have like this kind of exploits. And this slide is only not to show the payload and stuff, but it's to show that there is no authentication, no cookie, no nothing. You just like send your request and you get your connection back. And here, for example, this part on the right of the screen, that's a banner that you could use to fingerprint target online using Shodan, Census, FOFA, stuff like this. So it's useful for reconnaissance, recon. What I've shown so far is not the full audit. We found, like, as I said, command injection, and it's just part of the big picture. Beyond this easy primitive issue, we also find stuff like stack-based buffer overflow, heap-based buffer overflow, session management flow, post-out command injection, XSS, and many more stuff. But for reliability reason during a red team operation, our team, at least, we don't use unreliable exploits that may break a device. Because sometimes you're going to find only one target, and you don't want to break the only way in inside the firm. So we try to use very stable exploits. So this is where the individual bugs stop looking isolated and start looking like a systematic risk. Now, if we tie what we've seen, the fleet manager and the OLT side into one realistic attack chain, the early steps are about validation, getting it to the right position, and the later steps are about scale. Once you have code execution inside Cloud EMS or the management plane primitive or an OLT, the impact is no longer defined by one device. It's defined by what the manager can reach and what OLT is already controlled by design. Initial access starts from either side, an exposed OLT over the internet or an exposed cloud EMS, or maybe during a red team assessment, you will have access to the cloud EMS in a certain part of the network because it's lacking segmentation of stuff like this. So the chain works both ways because the trust relationship do. If I start from the OLT, I want to see what northbound connection exists and whether I can reach it from the manager. And if I start from the fleet manager, the scaling is already there because it's built to manage OLTs. So the key idea is that this relationship is bidirectional. First, there is the outage risk. If you can abuse configuration workflows and disrupt services at the access edge, You can take a large number of subscribers offline without needing denial distributed services, so DDoS. And the second, there is an ability to influence or observe the traffic at the access edge, which is already a powerful control point in the network, and that's what most of the time the APT will try to achieve. And finally, a compromised access infrastructure can become a starting point for further operation, because this device sits in a privileged part of the network, and usually they have weaker visibility and less monitoring than normal servers. So controlling the OLT gives you the influence over ONTs through OMCI protocol. So once you achieve this compromission of the fleet, you can attack the box of the end user through the OMCI protocol. So the impact does not stop at provider infrastructure. It can extend it to the subscriber premises too, and by premises I mean the house. Once you control the controller, everything is managed, become part of the risk. And here, it's not hypothetical, like we did it. We did it in lab, but it also worked for real. So I'm going to present the exploit chain and see this as a simple sequence or a red team operation. Recon, initial access, pivot, then scale. So the first phase is identification. So I fingerprint the target model. And it's not the most exciting step, but it's often that one that makes everything after work. Then you have the second phase, which is the execution. You trigger one of the pure authentication exploits against one OLT to compromise the management plane. And the only stuff you need to achieve this step is the network reachability, which we have from the internet-facing device. After that, I set up a stable remote access channel with a shell access and tunneling for the follow-up operation. So during the research and the real attack, we used the custom modified drop beer and the reverse SSH connection. So the main idea was simple. Once you have a reliable outbound channel, those internal management networks are no longer internal, and you can use SOCs to reach the fleet manager. Next, that we have pawned the OLT and we have our SOCs connection, we can use information leakage to fingerprint the cloud DMS server and identify the architecture of the target to see on what is running. So you can craft a specific implant, and then you can go to step 2 of the exploitation, compromise the fleet manager. So we use, I'm going to show a demo where I used a simple web shell, a GSP web shell, drop it, and got code execution in the fleet manager from my laptop. So once Cloud DMS is compromised, it becomes our pivot from the whole fleet. And I mean that now you can just either use the fleet manager as it's supposed to be used, deploy firmware updates, monitoring, stuff like this, or you can use, and because by how it's architected, I mean you can via SNMP reach all of the OLTs and bounce back through the fleet manager to reach all of the OLTs through SNMP, and then you can run the first exploit again all of the target and compromise the whole infrastructure. I'm going to show the demo at the end. So vulnerable OLTs were found in several countries. I'm not naming any ISP, but it was reported to different certs, and it takes us a long time, but mainly CERT-US and CERT-FR for France. The key point is that these devices are right now in real production networks, and they are still exposed. So the impact may vary by the context, but the technical risk is the same. Access infrastructure are high-values infrastructure, and treating them like low-risk internal appliance is a serious mistake. So I'm going to show you the demo now. Up. 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 Well, okay. So on the right side of the screen, you have what is supposed to be the fleet manager, which is right now unavailable. You can't access it. So we perform the exploit of the OLT in the first part. So I'm writing my implant. It takes a bit of time because we are writing it chunk by chunk. Then I know I have code execution. And what I do is that I extract from the configuration of the OLT the IP address of the fleet manager. And then I perform the attack of the fleet manager and create the SOX socket to reach the fleet manager. Now, what I do the part where I drop the web shell. So I drop my web shell implant. And as you can see, you can now execute command on the fleet manager inside the container. And the last step, but not least, is that it was not necessary, but we did it. We performed the Docker escape of the container and ended up like being able to execute command on the host. And how we did that, we did like through the Docker socket and the Docker API. Because we know the images and stuff, we spawned a new container with the host mounted inside the new container. And then we used, once again, the Docker API to reach from our container the new container. And we upgraded the connection from HTTP to TCP. And we got a shell inside the new container, which is meaning you got a shell on the host. So it's going to take a bit of time because I'm copy-pasting the commands. But as you can see, now I'm able to soon execute command. This is the part where I use socket to connect my container to the newly run container. So now I have a HTTP interaction with the target, the new container, and I'm going to upgrade the connection to get a fully TCP shell. So now we are in the new container, and I'm going to show you that you can retrieve stuff from the file system. Thank you. Do you have any questions?
So for the different vulnerabilities that you mentioned, including the pre-auth upload and whatnot, as I understood, because I'm not sure you said that the appliance or it's deprecated end of life, so like you didn't even do disclosure to the vendor, like
no, we did send the vulnerability to the vendors, and we had received no information. Mm-hmm. So we tried to go through CERT to reach from the vendor, and then we start looking at which, at the same time, ISP were impacted, and the CERT FR did not receive any information from the vendor, so they asked us to reach all of the CERT of the impacted ISP provider. So then we reached to, instead of going to each ISP, we went to each CERT, which is more convenient for us. And so we have no news. We just said to the different CERTs that we are going to publish at this date, and they said okay, because it was this work was 1 year old, yeah, because we had like kind of an embargo. We couldn't publish about it earlier. So technically, the OLTs are still exposed online without authentication, and we know there are.
Okay, so there is no CVE and
there is no CVE, so there is no nothing.
And there's, apart from this talk, there's no like write-up.
We did publish a write-up a few weeks ago. It's on Quarks Lab blog posts if you want to look at it, and the slide is going to be also available.
Any more questions?
May I ask something? Yeah. So now, if you attended both of the talk, you know how to go inside the ISP core networks, and then like you can use Pierre talk to escape from the from the backbone. And And you have a really complete full chain.
Yeah, thank you for your talk. So basically, we've seen that security lacks basic mitigations. Have you looked into the ONU or ONT firmwares as well? Have you found any interesting vulnerabilities there?
Actually, okay, I'm in the adversary simulation team of Quarks Lab. I'm not in the research lab, and the research lab were looking into the ONTs and ONUs, and you could exploit ONTs and ONUs through the compromised OLT. So
Okay, but no other way of entry than the compromised OLT.
Sorry?
The compromised OLT was the only way to get in the ONUs and ONTs. You could not access them from internet, let's say.
Ah, the ONUs?
Yes.
No, no, not to my knowledge.
Okay, thank you.
Any other questions? I mean, if not, you can still approach the speaker after the talk. Then give another round of applause.